So yeah, welcome to the presentation about soundness checking of realistic BPMN models. I will just go briefly over some slides and then show you the tools. I will jump a bit through the slides, so if you don't get all the details, let me know at the end, but I want to have some time for the Q&A and also for the tool demonstration. So let's just start the presentation here. So first of all, to introduce, we're talking about BPMN, and so I'll introduce the BPMN meta model and what BPMN is. Here on the left, you can see an example of a BPMN model. And in this model here, if you see my cursor, we have a process here on top, P1, which can start here. Then we have an exclusive gateway, meaning we can go either to this upper branch or the lower branch. We'll execute the right activity. Then we go to this gateway here, which merges the sequence flow. So whatever it's been done before, it doesn't matter. We follow this branch, and then we will wait for some message. This is called a message intermediate catch event, and then this process will end. And then there's another process which can start, which will send a message through a message throw event and then also can end. And BPMN is used a lot in the industry, basically by IT people and the business people, and they describe the business processes using BPMN language, which is quite nice since it's textual, it's graphical, so you can really, the two parties can work together to describe kind of the core process of a business. And then you can take this model, it's also executable, and you can implement it and run it through some both business process engines to then really have those workflows happen. For example, someone opens a bank account, and then you can say, okay, these steps I should follow. These are the steps I should take if someone opens a bank account. So this is one BPMN example, and of course, as model-driven people, we can draw the specific meta model, and that's what's also done in the BPMN specification. Here you can see is very simplified meta model describing essentially which boxes can be connected by which arrows and when does this conform and it doesn't conform. And the nice thing with BPMN is also you can persist this in an XML file, exchange it between different vendors since the BPMN specification is vendor agnostic, use it in different tools. And that's also what's done in the industry. So I can draw a BPMN model, persist it, send it to you. You get the exact same model with the same layout and run it in your infrastructure at the end. And then BPMN is also executable, so it has certain semantics, and usually these semantics are described using these tokens which flow through the model. And here you can see in this example here on this screencast that first the upper model gets started. So this is a simulation tool. Then we choose the lower branch. Activity B gets executed. Then the second process starts, sends a message to the first process, and then this one ends. So we really have the semantics of the BPMN and the syntax of the BPMN in the meta model here, and then the semantics are described using the tokens in the specification. They are not formally described; they're just textually described. How these certain BPMN elements should be executed. And since these BPMN models really become source code in the sense that they are also executed, you describe maybe the key business processes in your business using these BPMN models. For example, someone's opened a bank or in an insurance, someone has an insurance claim, someone hit his car and he wants to get reimbursed for this. These BPMN processes really must hold up to quite high standards, similar to source code. And to do this, we're going to do model checking, or this is what I'm doing in this tool, model checking BPMN. And the motivation is that some other studies have found many BPMN models contain control flow errors, which of course should be avoided because, as I said earlier, this BPMN is essentially similar to your code. It runs and it implements the key processes in your business if you use BPMN, of course, only. So there are some BPMN properties which are defined to uncover those control flow errors. I'll go briefly through those and then jump into the tool later on. So first of all, there's the safeness one. These are inspired by patronets, which are also similar, where tokens are kind of flowing through the model. And safeness means there's at most one token occurring at the same sequence flow. So if there are two tokens at any point and the same sequence flow, so the sequence flow are the errors you've seen before, then the property safeness is not fulfilled. Then there's option to complete, which means any running process instance must eventually complete. So any way through the model, any execution in any concurrent way, in any interleaving should always lead to a completion of the model. Then there's proper completion, which means each end event should consume only exactly one token. We'll look at this also later. And then there's no dead activities, which essentially means in any of the combinations of processes that are possible to run for one model, each activity should be executed at least once. If you now try to go back to the control flow errors, really what these properties are doing, the first one, safeness, is finding lacks of synchronization. So if you get two tokens at the same sequence flow, this means that you had a parallelization before, and then you had no synchronization. Then you just merge the flows together, and suddenly you get two tokens you didn't really synchronize. So that's what the first one finds. This can be an issue in control flow, but so maybe then you execute the following activity twice, not only once, because you weren't really synchronizing. Then option to complete essentially just checks for deadlocks that your process can always complete in any kind of execution. And then the first one, of course, that activities. If we draw the same analogy with that code should be eliminated. That activities are really like you think something, you have to do something in a certain case which is never reached. So either you eliminate that entirely or it kind of points to a different issue. And then we can check all of these things using essentially model checking. And I've done so with my previous tools. So let's just jump briefly into the tool I had, which will show you how this works. So here is my old tool, which is using basically you can draw a BPMN model. And then here we are doing two things in parallel. So these two things. And then if we here use an exclusive gateway, so we have essentially we're lacking a synchronization, and then we're going to the analysis and we check for the safeness, which should exactly find this lack of synchronization. Now this will take some time. So this tool, I will later on send you the link. You can also use it. It's deployed as a web application. And now here it's running on half a virtual CPU, so it's a bit slower. But as we should see now that this safeness should not be fulfilled. Let's just give it some more time. So I have to keep talking. Maybe this thing in the background really, yeah, okay, there it is. So you can see safeness is not fulfilled, but this really doesn't tell much to a BPMN modeler who's not really familiar with model checking and those kind of things. So that's what our new tool, which we essentially show in this demonstration later, is all used for. So now let's go back to the presentation, but we can essentially check all of these properties at the moment already. Okay, let's go to the next slide. So you can see that what I'm doing in my new tool is essentially similar. So you have the BPMN modeler, he uses an editor. Then we send the modeler to the soundness checker, if you've seen before, and we get back the soundness results. But the things that I want to do now is that I want to analyze every change that a user does to the model. And as you've seen before, it took some time to calculate all the soundness results and all these kind of things. So really, if we want to analyze every change, what we have to have is a soundness checker, which basically answers instantaneously. So in a very, very short amount of time, it should tell us if these soundness results are, or what the soundness results are. Are these things fulfilled, or are there some violations? That's the first thing we want to do. And then also you want to not just tell the user that something is wrong, maybe you want to also propose some changes. Like maybe there are some quick fixes similar to IDEs. If you have that code, there is an easy quick fix, just remove the code, or maybe there's a quick fix to change an if condition so that you reach this code. So we want to do kind of a similar thing. If we find some issues, we can try to find the root cause of these issues and suggest the user to do something. And then it's up to the user, to the modeler, to accept this proposition and fix the model, or just try it out, discard it, or whatever he wants to do. So we want to go one step further. So essentially we have three goals. First one, instantaneous soundness checking. Then comprehensible soundness checking. So you've seen in my old tool, it was not unsound, but you didn't really know why was it unsound. How did we get to this situation where there were two tokens on this flow? So it was a bit harder to understand what's going on. So we wanted to be more comprehensible for like a modeler which doesn't know anything about soundness checking, model checking, and all these kind of things. He maybe is only familiar with BPMN and these token semantics. And the third thing is this fixable thing. We want to go one step further and fix it. And this all really depends on the soundness checker. So the soundness checker has to be instantaneous, so it has to be extremely fast. It has to give us all this information about the soundness results such that we can compute these quick fixes, such that we can highlight what has been going wrong in the model. So really the secret sauce here is that the soundness checker is extremely fast and gives us all this information, which we can then use to make the tooling much better for the modeler. And I will spend a short amount of time for these three goals, and then I will show you the tool in action at the end. So let's look at this instantaneous soundness checking. So it's defined, instantaneous is defined in the literature, and this one definition I've used as taking 500 milliseconds or less. So if something takes less than half a second, it's instantaneous. And to validate this for our tool, we looked at three possible things. We looked at models of growing model size, models with a growing number of parallel branches, and some realistic models from the industry. I'll go very briefly through those. So for the growing model size, we had the following idea to test it. So we take 3 BPMN blocks, as you can see here in the slides. The first one is reactivities, the second one is an exclusive block, and the third one is a parallel gateway. And then you put these blocks in a BPMN model to generate increasing models. So here, if you look at a model with 3 blocks, you get each block once. And first you get a start event, you get an end event. And then we do this, but we generate up to 500 blocks. So if you have 300 blocks, you have each of these blocks 100 times. If you have 500 blocks, you have them even more times. And that's in this way we can kind of scale up the BPMN model always in the same way. We'll always take the same order of these 3 blocks, and then we keep growing the model essentially. And here the result is, if you run the test, that our model soundness checker really doesn't care a lot. Even at 500 blocks, the runtime is still at 10 milliseconds or less. And these models are so big that if you open them in the BPMN modeling tools, it's really those tools really take more time than we take to check those models. So this is really not a problem. What is a bigger problem is you have a growing number of parallel branches, and this we tested in the following way. We generate a model with n branches and a branch length of m. So this really is the worst case scenario for model checking, since we have like an exponential state space growth, and usually model checking is proportional to the size of the state space, which previously the state space wasn't increasing a lot, but the model size was getting quite big. And here we have complex models, but very complex models with a huge state space. And if we look at the numbers here, our checker is really only instantaneous until we have like 16 branches of a length of 1. And then it crosses its threshold of 500 milliseconds. But you can see here that already there we have 500,000 transitions and 65,000 states, so it's quite complex models, and then it just keeps increasing. But the question is, are these models often found in practice, these models with a high degree of parallelism? And according to this study number 7, those are quite uncommon. I think 2% of the models they found there had these kind of models, if I ever remember correctly. And even if they are found a lot in practice, we can still apply some optimizations using partial order reduction. So here we have some kind of mixed results, but seems to be still quite well for most of the models. And then we checked some realistic models. So the first 3 here are coming from the literature, and they essentially checked instantaneously. The state spaces are quite small, it's not really a problem. And the last 5 are coming from the industry. And if you compare this to what other people have been doing here, it takes more or less in the realm of seconds, 3 to 10 seconds, or 1 to 2 seconds on similar hardware, a bit less powerful hardware. Here I couldn't really compare them apples to apples, unfortunately. But this is instantaneous. This is kind of the necessary requirement that we have, and now we can really go to the tool. So how do we make it comprehensible? We show all the information we get from the soundness checker immediately in the model. I will show you this in the tool. And then we can also show counter examples in the tool. And then this will make it easier for the modeler to understand really what is going wrong. And then also we can do quick fixes in the model. This I will also show you now. And then you can apply these different quick fixes to your model. So let's jump into the tool again real quick. So here, this is the old tool. Okay. Yeah. Outlook wants to do something. I don't want Outlook to do something, so please get out of here. Here we switch to the other tool, and here you can see we load the BPMN model, and then it will immediately show us what is going wrong. So here we have safeness is not complete and proper completion, which are unfulfilled. And then to show which of these sequence flows unsafe, we have this annotation here of an unsafe sequence flow. So essentially this sequence flow will hold 2 tokens. And then we can look at the counter example by clicking on it, and we get this visualization. How did we get here? And we essentially get an execution log. How did we get there? Now there are 2 tokens sitting at the sequence flow. You can restart this, really reason what's going on, stop it, change the animation speed, or you can look at the other counter example, this proper completion one, where we now here we consume 2 tokens in the last event. So this is this part, and then always when you change something, it will always recompute. So if we change this to an exclusive gateway, it will fix this problem. It will immediately check again, and then everything has been fine. So this is essentially the comprehensibility part. And then the quick fixes are these green bulbs, as I shown before, and this will suggest that you can change this gateway to fix the problem. So essentially, you want to have the same gateways on both sides. That's why it's suggesting you 2 quick fixes depending on if you want to execute both activities in parallel or just one of them. And I will send you this link now into the chat, and it's also linked in the slides. And there are many more examples here which are a bit more complex. For example, here you add some additional gateways to fix the problems. But I think we have reached 15 minutes. This will really give you an overview of what I've been doing. So the paper is still under review, but all the source code is already public. Now I'm starting something again. So the source code is already public in basically all these source code. I will link this as well.